as I talked about in the introduction video, we get kind of limited in terms of what we can plug into the calculator. We can evaluate logarithm base 10, we can evaluate natural log, and those are two common functions we like to use on our calculator. But what happens when we have a different base that isn't 10 or isn't e? So that's where the change of base formula comes in. It allows us to change the base to 10 or change the base to e so that we can evaluate in the calculator. Now, it doesn't matter which one we use. We can either switch to base 10 or base e. It'll give the same answer in the end. I'll say I typically use natural log. I seriously think that just comes from it being a button that was easier to find on my previous calculator than log base 10. That might be it. So you'll find that I typically use natural log, but you can use log base 10. As we're typing into the Desmos calculator, it really doesn't matter which one we use. So how the change of base formula works. If we have a logarithm of base a of m, what we can do with the change of base formula is, if we switch it to base 10, it would be log base 10 of m over log base 10 of a. So the order matters here. So value goes in the numerator, base stays in the basement, goes in the denominator. And that's how I remember it. The base stays in the basement. So with that, we could also do natural log of m divided by natural log of a. But this will evaluate our logarithm for us, but using functions on our calculator that are easier to use. So if I have log base 2 of 5, what I can do is, using the change of base formula, I can evaluate this as, so we have our base of 2, value of 5. So 5 is going to go in the numerator, 2 is going to go in the denominator. But then we just need to choose, are we going to do base 10 or base e? Doesn't matter. I'm going to go with base e, so natural log of 5 divided by natural log of 2. Let's go to the calculator, and I'll show you this with base 10 as well, of how it ends up being the same. So if I type in natural log of 5 divided by natural log of 2, we get 2.3219. 2.3219. Now, how do I have any idea if that's correct or not? And get to this point where it feels like we're relying on our calculator almost a little too much. And we're just not sure, like, how do we know if that's the right answer? Well, if we have our logarithm up here, just remember there's one piece of information we're missing. We're missing exponent. So our whole question here is, having that base of 2, what exponent do we need in order to get out a value of 5? So what we just solved for here, this 2.3219, that should work as our exponent. So what we could do is check our answer by saying, okay, let's take 2 raised to an exponent of 2.3219. And it's going to be a little off because I rounded, but 4.99999. Awesome. That's basically 5. We're good enough there. So that checks our answer for us. So you can check these and simplify these by going back into exponential form. I have also done this without the, well, not completely without the calculator, but seeing an exponent of 2.3-ish come out, I would say, okay, base of 2 raised to about 2.3. Well, 2 squared is 4, so that would make sense for it to be 2 and a little bit more in order to get 5 out. So that 2.3219 would be our final answer for that exponent that we would need. Let me show you with if we did base 10 instead. So log 5 over log 2, we get the same 2.3219. So it really doesn't matter if we use the natural log or base 10 logarithm. All right, let's look at a few more of these. So log base 4 of 15. So what I would do is I'm going to do natural log numerator, natural log denominator. So base of 4 stays in the basement, so I'll go in the denominator, 15, and then we type that into the calculator. So natural log of 15, or base 10 log 4. It's a 1.9534. 1.9534, and that would be our answer. And what should happen is if we take 4 and raise it to an exponent of 1.9534, we should get 15 out. Which makes sense because 4 squared would give us 16, and we're just a little below that, so it makes sense that our exponent will be a little below 2. All right, log base 20 of 10. So we're going to go, actually let's do base 10 for this one. It doesn't matter, but I'll just show us a neat thing that happens with this one. So if I do base 10, so 20 is the base of the logarithm, so that stays in the basement in the denominator. Log of 10 is 10. And if we wanted to, we could simplify this before plugging it into the calculator, because log base 10 of 10, remember that's asking 10 to what exponent would give us 10? Well, that exponent we would need is just a 1. So really this is, in a simpler form, 1 over log of 20. If we wanted to simplify it a little bit, we could go that way. That wouldn't happen if we use the natural log, but again, we would get the same answer out. So 1 over log of 20 is a 0.7686. And that would be our final answer. All right, last one here. Logarithm base 5 of 1/2. Let's go natural log of 1/2 over natural log of 5 and plug that in a calculator. Natural log of 1/2 divided by natural log of 5 is a negative 0.4307. And I like to do that one to show that we can get negative numbers out. And why is that? 5 to what? Yes, let's do this real quick. Equals 1/2. Typically, if we're starting with something that is, my screen will focus, there we go. Having a whole number, or rather a large number base, a base that's higher than 1, if we have a base like this and then our outcome is a fraction, that's a property of negative exponents. So just as a refresher with negative exponents, like if we had 5 to the negative 1, that's 1/5. If we had 5 to the negative 2, that's 1 over 5 squared, which is 25. So negative exponents, they make these fractional values by moving our calculation to the denominator. So you can have negative outcomes, and it's specifically this relationship between the base and value, where the value ends up being a fraction between 0 and 1. So that's our change of base formula. It just helps us plug in things into the calculator so that we can simplify and solve.